Good morning, good afternoon, and good evening, everybody. I'm Xiang-dong. I welcome you to join our webinar series, Air Pollution and Human Health. And last week, we had lecture on air pollution and central nervous system diseases from Professor Kaja Kenyon. And today, we are going to have the 10th lecture, Differential Toxicities and Contributing Chemicals in Urban PM 2.5 of China. The honor speaker is Professor Xiang-dong. Before getting started the lecture, I would like to give a short introduction of Professor Li. He is the Chair Professor of Environmental Science and Technology and an Associate Dean of the Department of Civil and Environmental Engineering, the Hong Kong Polytechnic University. Professor Li finished his PhD study in Imperial College London, United Kingdom, and he has broad range of the research interests, including air pollution and health, regional pollution, urban environmental study, and soil remediation. And Professor Li has scored fruitful achievements. He has published over 200 SCI publications with 14,000 SCI citations. He is currently the associate editor of two great journals. One is Environmental Science and Technology, and the other Applied Geochemistry. He's also the editorial board members of National Science Review and International Journal of Phytoremediation. Let's welcome today's speaker, Professor Xiang-dong. I'm gonna hand it over to you.
Thank you. Thank you. Thank you, Professor Zheng's kind of the very kind introduction. And I'm really glad to have the opportunity to just to present some of our recent study, which we're using about this in vitro cell toxicity test to study about this contributed chemical in the overall toxicity in urban PM 2.5 of China. So before I really go for the next slides, I just wanted to acknowledge our co-author because it's really a true collaborative project. And so we have quite a number of first author, Dr. Jin is my postdoc in my group. And Jiawen Xie is kind of my PhD student, but we do have a collaborator like Professor Xiaoshan Luo, and from Nanjing University Information Science Technology, and Professor Chris Wang from Hong Kong Baptist University, and we have Professor Ralph Zipman, which actually based on the Helmholtz Syndrome in Munich. We do have about two colleagues from Professor Jun Li and Professor Gan Zhang is Guangzhou Institute of Geochemistry, Chinese Academy of Science. We do have another collaborator, Professor Pingqing Fu, and from the Institute of Surface Earth System Science at Tianjin University. Okay, and anyway, I thinking I will running very quick. In probably like in the general introduction, I believe in a previous lecture, you all know this quite well, but just a very quick review on what is global significance on air pollution, PM pollution. So you can see about roughly we have around about over 90% of the world population was living in place which WHO air quality guidelines are not met. And you probably see most of them consider about a very elevated concentration of PM 2.5. So there are many of different numbers, but most recently WHO in the last year number, which attribute 4.2 million of premature deaths, and which attributed to about ambient PM 2.5 pollution. So that's quite a number of them in kind of a Southeast Asia and West Pacific regions. So you can see there are many of the issues regarding specifically the health problem associated with about whatever the air pollution and health issues You can see regarding about this heart disease, stroke, regarding about the chronic obstructive pulmonary disease, COPD, or they come from about lung cancer in the long term. Okay, so some of you visited Beijing, China. You probably about want to enjoy about is a morning like a flag rising ceremony. But on an unlucky day, you will see there the whole most famous landmark is gone. So you're probably using about to draw about what is the shape of the Tiananmen Square monument there. But anyway, PM 2.5, we all know is quite a complex mixture, and from a very much of these chemicals, either in this kind of SEM, scanning electrical microscope picture, you can see about this kind of like sodium-rich particles. You see about quite a number of these minerals. There's kind of sulfur-rich organic compounds. There's metals, there's fly ash, there comes from black carbon on the chute. So they are really regarding about this kind of like pollution, environmental pollution in China. The air PM is probably is one of these most significant single environmental issue. Consider they have a unique pollution characteristic. They have a long-lasting period, probably within the last 10, 20 years in China, and have a high pollution intensity. Some of this almost record like so far regarding about PM 2.5 from the high volume like a sample we can have. And this also cover very large geographic coverage regarding about sometimes the whole like 20-30% of North China was by this kind of this very significant haze state. So there also have a recent study. This kind of the issue was really complicated by very global climate change. So in other way is, and the air pollution haze was both considered with about anthropogenic activities and also which have considered within about this climate change regarding about the precipitation pattern, regarding temperature or other things. Okay, so if we looking about into the last probably 5 years, I mean, from the government effort, from this kind of the strict regulations, you can roughly see about the general decrease trend. This is what we have one very short review paper, which published last year, which have about consider from the last, this number is on the national average of PM 2.5 microgram per cubic meters in almost 300 cities in China. So like this average concentration have the drop, but still actually haven't reached the national like a standard, which is supposed to be 35 microgram per cubic meter. But if we reach to the like a final goal for WHO standard for 10 microgram per liter is a very long way. So that's about how the situation you can see for right now. Bear in mind, this about this whole national average city data. If you compare about very polluted cities, this far more higher than this number indicate. Okay, so within that in mind, our key scientific issues we want to cover is consider how about the different like toxicity per unit of mass PM 2.5? Can they actually using one single data, toxicity data, to project the health outcome? But anyway, you can see from about this kind of like paper published in Nature, which back about 3 or 4 years ago, and when they have using a global burden of disease back 2010, there's regarding about this outdoor air pollution, majorly by PM 2.5, and they have one of the claim from also we primarily assuming all the particles are equally toxic. But as you can see from our chemical knowledge or about the study calculation of PM2.5, hardly this can be true. So I would probably give you two examples. The one is about this epidemiological evidence. There's one paper which published kind of like 2 years ago, which have the find particular air pollution and the daily mortality here. So one of the conclusions drawn by the author is like this national-wide analysis, which almost cover about 272 representative Chinese cities, found that there's coefficient expose and response relationship in China was lower than the recorded in Europe and North America. So particles may not created equal in terms of their toxicity in different parts of the world. Consider about this emission source, like atmospheric process and other things. Okay, so just to draw from that particular publication, you can see there's daily concentration of a particular region, like Northeast, North China, East China, and the Middle South, Southwest, and Northwest. So some of them actually have a close correlate within about concentration of PM2.5. Some of them are not exactly, some of maybe dipping, or some of at early, like a lower concentration compared with a high concentration. So that's really have illustrate their exposure response disparities of PM2.5 in different regions of China. They are actually, the fine particle may not created equal in terms of toxicity across even one country like China. So there's a second example I want to just present here is there's also a recent study, which the paper published also 2 years ago, which have in using about animal study, which have about conducting about in vivo evidence, where like PM2.5 collected in Taiwan, China, and collected in Sacramento in California, was actually using a same amount of total loading to feeding about this small mouse, and afterwards, after 1 or 2 weeks time, they come over for about all these different biological and biochemical calculation. So the interesting point is there's a greater land toxicity for California PM2.5 than the really coal burning and in Taiwan, in North China. But that have to be at equal mass concentration. But you probably know Taiwan one was far more like higher concentration than the California one. But anyway, the different like toxicity appear to be driven by like the high level oxide organic carbon, and also by a greater copper content in a California PM2.5 compared with the Chinese one. So which do they really play a role, and to what extent? That's what we want to know. Okay, I will also put in another dimension. This the diagram we plot from the WHO, like kind of like a annual report. This back to WHO report in 2016. We have all the country data. The country data considered with the population with like annual medium PM2.5 concentration. And here is about age-adjusted annual premature deaths attributed to outdoor PM2.5 pollution, which about 100,000 people. So you can see there's very interesting patterns. In the yellow dot, we have many of these high PM2.5. This is the annual like medium value of particular monitoring station. And the blue dot actually is the countries who have about the high concentration, but on general also have a slight higher kind of the this age-adjusted annual death. But there's also some countries which about this Central Asia, Southeast Europe, and the former like Russia, Soviet Union, which have about relatively, they have a lower annual like a medium PM2.5 concentration, but also they have the significant higher like kind of age-adjusted annual death. So that's triggers to consider. It's not only for like within one country like China, but also there are significantly crossing the world, crossing different countries in the world. There's about toxicity and the final like health outcome can be different. So you probably see also I particularly highlight the two most populated country, China and India, is somewhere here, which with a significantly like a kind of a PM 2.5, but also have a higher, relatively higher about this premature death considered within like a kind of age-adjusted like a number. Okay, so that's putting us in the hypothesis here. So we do consider about what is the physiochemical aspect for PM 2.5. We have this contrasting emission source, and this one was published probably a couple of years ago, were categorized about 3 major cities in China, Beijing, Shanghai, Guangzhou, and also Xi'an. So come about from north, northwest, and the east and the south, which have quite a significantly different like a PM 2.5 concentration. Consider most polluted in Xi'an, and then relative in Beijing, and then probably in Shanghai, and then about in Guangzhou. So, but you can see the profile, chemical profile, the composition-wise, they have quite a significant different like source. For example, you can see here like significantly about in Xi'an with unidentified composition, significant organic like composition, and there are others. But if we're looking about using the chemical profile to apportionment the major emission source and factor, we also can see quite a significant difference. For example, about the second organic, like secondary inorganic rich particles contribute significantly in about in Guangzhou compared either from Xi'an or other like Beijing. So that's about really consider this kind of chemical profile really trigger there's a kind of a different toxicity like profile, or even causing about a various toxicity potency for PM 2.5. Okay, so that's about leading to our scientific hypothesis for all this study. PM 2.5 particles are not equal toxicity either by this in vivo or epidemiological study, and the regional differentiation of PM 2.5 considered as equal mass concentration can be detected most sensitively. We can using about in vitro cell toxicity tests can be as a result for verifying concentration and chemical composition of toxic compounds. So that is about key like a question we're going to ask. Okay, so the tour of 2 cities, like Dixon's like a novel title, we have in a study is we have a collecting one of the typical north part in Beijing, and also about one in Guangzhou. But this one sample campaign was conducted quite a number of years ago, which about in January back 2014, which record a very severe winter haze event. And we have the daily 24 hours sample by high volume sampler, which you can see about this color of the PM membrane we collected. So for some of you who was not very familiar within these 2 major cities in China, I'll just very quickly give you about this introduction. Beijing about around about the population around 22 million, and the urban population, which dominated by monsoon influence continental climate within very cold with cold and dry winter. But for the Guangzhou is around the population around 50 million, and then there's kind of very typical like Hong Kong is subtropical climate influenced by the East Asia monsoon, and with mild and comparatively relatively dry winter. So you can see how about this clear day and hazy day in the same location. Anyway, so let's looking some of the fundamental like physiochemical feature here. And if we're looking about the mass concentration of this 2 weeks sampling campaign, So the average in Beijing by that 2 weeks time is PM2.5 is around about 200 microgram per cubic meters, but in Guangzhou probably around about 96 or half of this kind of Beijing number. But if you consider about the maximum range, the Beijing one have a much far more severe hazing day. So in other words, if we only compare about this average concentration during the 2 week sampling campaign, so if assumingly equal toxicity for equal mass concentration assume, Beijing would have probably about twice exposure risk for PM2.5 in comparison with Guangzhou. But if we wanted to do is we taking about the same mass amount, both from a sample from Beijing and Guangzhou. We're doing the cell variability test. We also have consider within about this relative like oxygen species, like ROS one, and relative to the control. You can see the control one, where about this gray shade area, either you have about increased PM2.5 concentration, they haven't changed. But if you're using the real sample from like the blue one from Beijing and the red one from Guangzhou, so you can see when they are reached in certain point, the line was really significantly different. So like the Beijing one caused much higher like a cell variability. And the same case, and the line after a certain PM2.5 concentration, even over in a very low side, you can see about there are significantly different pattern regarding about the Guangzhou compared with Beijing, significantly higher, causing about reactive oxygen species. And so in other way, if we're using this one, consider we have a differential toxic potency for the real concentration. Consider about this total concentration compound about cytotoxicity potency, oxidative stress potency. So there are more profound exposure risk in Beijing, probably times 4 times 6 of PM2.5 on the real exposure issue. So now we're facing the challenge is we need a more integrated toxic indicator for direct relevance to human health outcome, which truly can adjusting about this mass concentration PM2.5 and the different chemical profile. So that's leading to our further work. So we analyze this about concentration of total pH per unit of mass PM2.5 in Beijing, which you can see the Beijing one is this particular pH is almost about 10 times than the Guangzhou one. But if you're looking about the metal and metalloids and so heavy metals, so the concentration is around about 5 times different. So that's about how this particular like nature of the chemical part. Okay, I believe most of you know if we are using this like a cell toxicity test to like measure about overall PM2.5 like toxicity, we can only getting a tip of the iceberg, because what we can quantify, for example, like the previous slide I show you, for the pH, we analyze around probably about 15, 18 different pH. Or for the metal side, we probably have over about 10, 20 different metals. But compare about the whole PM2.5 particles, they may have over 1,000 or even 10,000 chemicals in a really kind of a chemical kind of like cocktail. So what we want to do is if we can quantify the major known chemical content, then there's whatever chemical analysis regarding metals and the pH, and then we have known some of this concentration of the kind of like analyze the metal or pH. Then we're leaving this one, how toxic is each individual known chemicals. For example, we have a metal copper, metal arsenic, metal whatever, and we have the pH on consider within probably about 15, 20 countingers of the pH. Then we want to see, okay, if we want to using one single metals, how that metal can contribute overall about the whole, like this kind of overall toxicity for about this chemical mixture. Okay, so in the left-hand side, we try to do is we're using this bioanalytical assessment. So in this one, we try to using a biological effect. For PM2.5, we're using one reference material. The reference material to simulate how much the reactive oxygen species IIS generation, because that's the most important surrogate where we can use it to testing the overall toxicity. Okay, then using this kind of like a biological equivalent sample, we define as a BEQ. Then we can analyze how much the effect explained by individual metal or pH. Then we putting that together like the mixture toxicity of known metals or pH, and we can have quantify about mixture toxicity prediction using about validation of concentration addition. Anyway, I would explain in the next few slides. Okay, what is a biological assessment of PM2.5 samples? So bioanalytical equivalent like a BEQ concentration, we're going to use express the mixture effect of giving sample containing some of unsolved chemical component against a reference compound. So this reference compound we selected most likely, which called a TBHQ, is like tertiary, like a beta hydroquinose, is a very known reference compound. In this case, as can generate IIS induction. So we compared each about the known metals or each about this pH compounds. Then we calculate how much the like TBQ numbers regarding induction ratio for the IIS from relative to the control group, and we can calculate if there's a like a EC concentration about is 1.5, introduce 1.5 time of this relative to the control, we define there's a kind of effective concentration. So in this case, we have a calculate each about the PM2.5 we collect from Beijing and Guangzhou. Okay, so then if we are putting a long story short, we can put in about all the relative ranking. For example, about this chromium 3, iron 3, zinc, like this BP for about one of these compounds from pH, and compare some of these compounds like double BAP can be about, you can see the roughly toxicity among this compound around 5 magnitude difference. So you can see from the low toxicity compounds into the very significantly high concentration, high toxicity compound, because maybe the concentration are low, but their toxicity potentiality is high. They may play a very important role in the overall PM2.5 concentrations. Okay, so before we can really quantify this toxicity like issues, we need to put in a little bit of consideration is how we all know these compounds we all have analyzed are into a very detailed concentration. We're putting them in a summation of each individual compound as toxicity. Then we mix all the compounds together as overall like original PM2.5 or totally mixture in these chemicals in a solution in a lab. Then we're going to see if this individual combine equal to the overall like mixture. Then we can see, okay, if I deduct 1 or 2, can they actually know if the cadmium, copper, or like a BP or BQF can really, how much is 1%, 0.5%, or 20% toxicity to the overall PM2.5? Okay, so Then we're going to do, okay, the right part balance, we need experimental determine combined effect of identified metal and pH, compare our concentration defined mixture, compare the real sample, we can have about this definition. Then on the left-hand side, we have the predicted combined effect for identified metal pH in the mixture using about like concentration addition CA model based on a concentration effect curve with individual compounds and with some of the molar like composition for individual component detected in the sample. We have a calculate in the concentration compare within about this ROS generation to the control group. Whatever here, the two example about copper and BAP. Then we making about all this into about predicted quality over 25 mixture within -1 +1 range, mean a very good in agreement between the experiment determination and the model prediction. What we have is, if we're using CA method predicting each of the total quantified compound, compare with the overall combination total mixture, they agree quite well. You can see about this, both the line for the CA and the experiment line. So then we can say, okay, now if this agree, we have about quantification of the concentration, we have their overall individual chemicals, then we can calculate each of the chemical can contribute to the overall PM toxicity. Okay, so let's put in about this in a real test. Okay, if we know about the metal concentration in Beijing, probably about in the total mass concentration is only about 5%, 5.7%. But in Guangzhou is only 1.6%. But if we are putting about this, all the metal effect into about overall toxicity, you can see about the contribution for the metal side in Beijing is about 11%. But in Guangzhou is about 7%. Okay, so because we have a combined all the detected metal in here, so this probably the first time we can quantify some of these compounds in the experimental, well-defined experimental settings for PM 2.5 toxicity. Okay, so the same story we can do is, because not only for the overall metal, we can actually have each about, in this case, the 10 most relevant and abundant heavy metals or major elements like iron, other things here. Interestingly, both the Beijing and Guangzhou, although they contribute a different toxicity overall contribution, but all these three metals, iron, copper, and magnesium, are this major contribute, almost 85 to 90%. So they are the most three dominant elements which active for intracellular ROS formation. And also there's a kind of consider is this transition metal dedicate about this oxidation potential in the whole toxicity test, and not about our traditionally regarding cadmium and chromium and something like lead or arsenic, because both of these three metals have this you probably all know they are very redox potential, and like iron, although toxicity is low, but the concentration is high. So you need to consider both potential toxicity, consider with the total chemical, total loading in the particle. Okay, so the same way, I have really needed, taking about the time, we can do the same case for the pH, the organic pollutant here, but in Beijing, you can see they have contributed about 27% for the overall toxicity, because there's a high total loading here, but also they have about specifically from the winter coal burning for the central heating back to about 5 years ago. But for same as for Guangzhou sample is about 17%, because the total pH also is only probably about 10% of the total loading, like in Beijing. So the same case, we can do about roughly around about 12 individual compounds we have. So you can see the most of the contribute one here is about the DALP compounds, which normally not quantified as US EPA priority pH, but their one contribute almost 70 or 65% overall. One particular compound compared with all other probably 11 or 10 different compounds are. So this is the most dominant driver. And then, for example, if we without like an elected without analytical data, which may leading more than probably around 10, even 20 of overall effect and unsolved for this toxicity. So that's about the issue. We still want to know it, because all this is still about the parent pH. We still want our next stage to do something like this further whatever degraded or some of the other like metabolites compounds to see they have a change from these parent compounds to the overall toxicity. Okay, but anyway, we can further putting about is a long-term cancer risk assessment for this using about this sampling period as guideline, and we can roughly calculate about 70 years lifetime exposure. And as you can see, and so the Guangzhou one, which actually within WHO accepted risk value, quite agree, but the Beijing one is almost 10 times higher than that. But bear in mind, this is the worst scenario. We're using about only for the hazy day rather than like the annual like data. But we have calculated right now for the Nanjing and Guangzhou for about different season, which is more realistic to assuming some of the long-term 70 years exposure. Okay, so the last part I might touching a little bit. You probably see, okay, now even we have quantified total metal contribution, quantified some about combined effect for the pH, but we still have a large unsolved pie here. So for the Beijing, there's unaccounted for 62%, and for Guangzhou even higher, about 76%. So that's about what is either the chemical we haven't quantified or there's other contributor. So I want to just give you have a looking about our kind of a last probably about a new data we have putting on, because we almost exhaust so our Beijing samples for about this toxicity test. We're using another city, like we have a 2016 winter sample from Nanjing, and we have a Nanjing and also Guangzhou the same time period comparison. And you can see how about this, we are also focus on some of the not only physiochemical aspect, but in this time we are using about endotoxin and as a kind of like a microbial contribution towards the total overall toxicity test. Okay, so anyway, I skip about the detail of the chemical microbial analysis side. If some of you are interested, I would give you about a reference in. Okay, so if we put in this one, like same as our Beijing and Guangzhou comparison, but this is the Nanjing, you can see metal contribution, pH contribution, and compare about this also, this is the IIES. This considered is induced inflammatory response. And here, quite an interesting part, you will notice here, there's endotoxin microbial contribution is almost more than the combination of metal and the pH. In other way, so this kind of the small bacterial microbial contributions can also contribute around about 25 to 30% of the overall toxicity. So the bi-aerosol can contribute significantly to about a major toxicity. So if we looking even, because most this endotoxin come from about gram-negative like bacteria. So this you can see how about the Nanjing one and have a higher than the Guangzhou for the gram-negative bacteria. We also majority of them is like a proto bacteria, which have like the phylum which can dominate about this microbial community there. We are still focus on there's new seasonal change and how their interaction with this chemical, like physical chemical, like toxicity. Okay, so I thinking probably I'll be using the last few minutes to making a very quick summary. So the conclusion, general conclusion remarks, I hope I can demonstrate there's equal mass concentration PM2.5 does not translate to the ecotoxicity. So due to there's a different like a chemical mixture composition, and so the assumption of the ecotoxicity all particle will underestimate or sometimes overestimate their site-specific populating health risk. So unequal particle toxicity would modify this exposure response curve in a different region or even different cities, or even the same city as a different whatever kind of like specific exposure pathway or emission source. Okay, if we are using this mixture like toxicity modeling, like the BEQ and bioanalytical equivalent approach, we have a provide of almost the first time and a quantitatively approach to estimate there's a compound specific relative contribution to the PM2.5 overall toxicity. We understanding there's a complexity, there's a different like a complex mixture, but we can actually estimate their relative contribution. So metal and pH are important toxicity component, but may not as dominate as we previously perceive or report, because in the past kind of like a study, most people actually linking this concentration and by the correlation analysis. We all know correlation analysis not a cause effect. It's only kind of like there's have some occurrence rather than about the cause. If our BEQ one, which actually review some of the direct relationship between about this chemical profile and this toxicity response. Okay, so a few further study we are right now, and also some people are interested to conducting. We need a more integrated toxicity indicator for the relevance of the human health outcome, which can adjusting the mass concentration of PM2.5 for more accurate exposure and response assessment. And we also need to combine the toxicity evaluation for both chemical and microbial component. You probably see one of my examples for the endotoxin and can contribute even more than the combined metal and pH compound. So we still need to have a more broad spectrum identification, because we still have about unsolved toxicity driver by combining some of the targeted and non-targeted analysis, or high throughout toxicity profiling and the prediction, and some of the mixture toxicity modeling in order for about health-oriented and prioritizations of the mitigation target. For example, and the mitigation pH or heavy metals or others by 50% would result how much the decline, which about the total PM2.5 as particle toxicity. Because we are current using real PM2.5 data in that 2 weeks hazy day. But if there are different season, the microbial like composition can be different. We still need to understanding there's kind of the mechanism, there's contribution to the overall toxicity. Okay, so that's about our, want to acknowledge some of our funding agency, both in mainland China and Hong Kong and our university as well. I thinking some of you want to know much detail for my talk today. Here is like this EST paper published, I believe is about 3 or 4 weeks ago. And you probably can have all this kind of very much detailed methodology and interpretation. And there's almost 50 page of the supporting information for you to understanding the method and the final interpretation. Okay. Some of you may interest to know, and we have probably about 2 years ago, there's one kind of like a critic review, and we have about on airborne particulate matter pollution in urban China, a chemical mixture perspective from source to impact. So that's kind of, we have review very significant, very critically, some of this like online and offline analytical like method, and some of this like health side. Okay, so the last but not least, some of you are interested for the microbial one. This one of our first paper considered with airborne bacteria and some of the antibiotic resistant genes. That's another like a follow-up considered within about urban and the rural side. We also have a follow-up quite substantially for the other side. Okay, I thinking probably that's as far as I wanted to introduce today. I really appreciate your like kind of presence, and really glad to have opportunity to talking to you on our recent study here. So I thinking I will back to Professor Xiaowen Zheng for a bit of this QA question. I'm more than happy to answer any question you may have. Thank you very much.
Thanks for Professor Li's brilliant talk. It's very impressive. It gives us a good story and on how to quantify the mixture, the toxicity of the PM particles. Now we are opening for questions and answers. You can post your questions on the chat box on the right down of the Zoom panel, or you can speak directly to the speaker if you have the microphone. Well, we have the question from Dao.
Okay.
Can you explain why the PAH contribution to IIES in Guangzhou is approximately two-thirds that of Beijing, when the concentration is only 10% of that in Beijing, and
okay.
individual toxicity of the various compounds is approximately the same?
Okay. Okay. Yeah, I think that's a very good question. I believe the issue regarding how the two major pH compounds, although you are right, the total concentration in Guangzhou only 10% of that total pH in Beijing, but for the two most toxic compounds, the concentration-wise only half of that Beijing. So they can still contribute significantly, like overall contribution for the PM2.5 concentration is two-thirds of the overall contribution of the Beijing. That's a very good question. That's exactly the way, and if we only rely on the total concentration of pH, we cannot find about the driving force for the real major contribute for toxicity. That's a very good question. Joan, do I need to write in a written reply, or I just talking about on reply Professor Evans on this?
Yeah, that's great. Just talk.
Okay. Okay. If
you don't need to write.
Dog need about my written reply, I can do it. But anyway, I will leave you take a question first. That's a very good question. That's absolutely very kind of a detailed like observation on that. Yeah.
Thanks, Professor Li. Is there any question from the audience? Well, actually, I have one. This is one for you. Well, I totally agree that the in vitro experiment is a very good method to do the toxicity screen. And well, I have the one concern that do you think is there cell-specific toxicity, I mean, when we use the model, how can we choose the cell? I mean, we have different kind of cell, the organs, the cell. So when you use the in vitro toxicity determination, so test, how can we?
Okay. Professor Zheng, that's also a very good question. I thinking the way we are using for this current study is about the A459 for this human esophageal cell side, because this one are quite like sensitive and can really simulate our kind of the human inhalation toxicity. When the particle getting into our respiratory system, the first one they actually is going to direct deposits on the cell. So that's why we have to using this kind of like the direct contact cell as a simulation for our human biological response. So you are right. We need to unify about the cell species and the cell generation to making about the comparison of the toxicity test. So you can also selecting other cell as well, but unless you know the cell well, they can reflect most of the sensitive ROS generation, and you also need to making sure the cell exposure condition are very same as among the different samples. There's one new development in our group is we have going to install in vitro LA system, air and liquid interface, which actually probably about in 2 weeks time. And so that one is going to, you can see, I haven't gotten into detail. The current study, we have still using the cell in a solution. Then we have introduced the particle to the cell surface. But now the like the air and the liquid interface is the solution, the cell actually on top of the solution. So is the particle going introduced to making direct contact with the cell membrane. So that's exactly is our kind of upper respiratory system. So, I mean, although there's a kind of some of the fluid, but the cell actually can be in direct contact within like the solution. Yeah, so that's can do. We want to also try to do is we want to move this cell from lab into the roadside. So as long as we have the mobile lab, can keep the cell health, and in the long term, we want to do about in situ real-time exposure. Like probably if you know at our university is close to the very high like tunnel cross harbor tunnel side, and we wanted to move a small like a mobile lab to do some about 2 or 3 months real-time exposure. But in the same time, we are do the chemical profiling using like aerosol mass spectrometer. So then we can demonstrate real exposure on site with chemical profiling and biological response.
Oh, that's great. That sounds great. Right, you can do the institute cell experiment. Wow, that's
that's a bit of a challenge. But currently we're using this alley. You probably see I needed to specify because the current ROS generation is based on 4 hours testing. But for our one, I mean, cell, that's normally okay. But if we want to really have this human impact side, we probably like, you know, if like Beijing or even in Guangzhou or Hong Kong, so the haze can be for the 1 full day. And then when the weather improved, the haze gone. Then come over for another probably 3 days or 4 days. Then there's, so we have this long-term but intermittent exposure. So that's why we want to try to train our cell to adopt this kind of long interim exposure. So we're putting them in 24 hours, or even now we do 48 hours already. But we then back to the cell incubator. Then after certain days, we putting them back again. So we already observe if the cell already pre-exposed to the stress, whatever haze day or PM2.5, they actually less cope than the fresh cell. So the same case, you can see about quite a number of study in whatever in Canada, US, or in Europe, where about this whatever significant health effect compared with environmental like exposure, they always have time lag. So for example, in Guangzhou, there's a study for cancer, which about 80 or 10 years lag, considered with the peak of the PM2.5 exposure, because that's about how you have some of this kind of like cell response less to cope with the new environmental stress. Yeah.
Okay, I see.
I probably going too much. Okay, I saw there one note coming.
Another, right?
Yeah,
another question.
Yeah, another one. Okay, I read out the question first. So I'm starting experiment to expose the cell to gas from indoor particles, and can you help me with some setup? Okay. Yeah, that's interesting. For the gas phase, I'm still confused here. Are you purely for the gas phase, or you also combine with the particles? Joka? Okay. I first whatever you okay. Just gas phase. I thinking, yeah. You can do is you need about your exposure chamber to set up without leaking the gas. So I believe if you I properly can send you, I give it to Hoy on the probably pass you. If there's one manufacturer in Germany which have a small unit for purely gas phase, you need about a denuder or other things to into your gas phase. Then after you expose to gas phase, you're going to see how this biological response and the biochemical change. I hope I answer your question on that. Okay. Yeah, please, if can drop me an email, I will send you the detail on that. So the next one from the WeScan, and so what are the normal concentration we'll see in this measurement? Good question. Because currently the study, as you can see from our title, we are focused on the PM2.5. So in other words, we are focused on the fine particular phase. I mean, although I fully understand your question, so during the hazy day, the VOC and the other gas phase, like whatever in Beijing and Guangzhou, is a nitrate and sulfur and others, or even whatever other phase, gas phase, also high. But we are currently only do the fine particles. So also, as I introduced to Professor Zhang just a few minutes ago, we want to do the air and the liquid system to combine with the gas and particle. But that have a still need a little bit adjustment for the experiment setting. We may reporting some of the result, I thinking by end of this year, because the equipment that we're shipping to our lab in about 3 weeks time. Yeah, you are right. We have a one proposal actually addressing both combined effect from gas pollutant and also PM. I also want to making one more point, because in Guangzhou and Hong Kong, not only for the VOC, we also concerned about this ozones O3, because that's in the whole Guangzhou, Shenzhen, Hong Kong, and Macau area. So whatever we call the Great Bay Area now is the major issue, not only for PM 2.5 compared with the north part of China. We're doing a better job now. But there are still a way we want to do further kind of like elaboration, some of this kind of like ozone with other precursor for the air pollution. Yeah, good point. Okay, Jacob. Yeah, I get your email and try to send you some more further information.
Thanks for Professor Li's impressive talk. And any other questions from the audience? Well, if not, we have to thank Professor Li again, and thanks for your effort and your time to give us a brilliant presentation. And now I would like to remind you that our last lecture of this current series will be held in next Thursday, not Wednesday, because May 1st is the international holiday. And the last topic is occurrence and toxicity of indoor air pollutants, advice on a healthier living style from Professor Ray Li. And I'll catch you guys on Thursday, May 2nd. Thank you. Thanks, Professor Li, again. Thank you.
Okay, thank you, Xiaowen, and thank you, Hoi. I really enjoy the experience. I mean, although about whatever 700 miles away, and we are really keeping a nice classroom atmosphere. And just please drop in the email or any of your questions. We more than welcome to making further exchange regarding your research outcome, regarding our research group. And we're more than happy if you have a chance to visit us in Hong Kong or whatever other occasions at whatever conference or other occasion. Okay, thank you very much.
Thank you, thank you.
Okay, bye now. Hi, bye, Xiaowen, and bye all everyone. Thank you.